Don't forget to full screen on the slides.
I will.
Okay.
The broadcast is now starting. All attendees are in listen-only mode.
Hello everybody and welcome to today's webinar. The subject of today's webinar is going to be TracePro's Monte Carlo Raytracing Methods and ways to reduce statistical noise, memory usage, and your ray trace time. The presenter for this afternoon's webinar is going to be Mike Govin, our Vice President of Sales and Marketing here at Lambda Research. I'm Dave Jacobson, Senior Applications Engineer here, and I will be acting as a moderator. As we go along, if you have any questions during this webinar, please feel free to submit them using the questions box in the GoToWebinar control panel. And also this webinar will last about 45 minutes or so, and then we'll follow that up with a 10 to 15 minute question and answer session. So with that, I'm going to turn the proceedings over to Mike. Mike, all yours.
Thank you, Dave. In this webinar, we will introduce the Monte Carlo method that's being used in TracePro. I'm hoping that I can have you understand how we can reduce statistical noise using variance reduction techniques in the product. I'm going to show you methods to speed up ray tracing, use less memory, and show you a couple of different ways of doing tracing in TracePro using both a splitting and non-splitting mode. And finally, to understand how to do reverse ray tracing in the product. If we take a look at the Monte Carlo ray tracing and sampling used in TracePro, we use a Monte Carlo calculation technique where this is named after actually the city of Monte Carlo, where you have a casino, and pretty much it is a simplest form of a probability experiment. So in other words, if you had a dice and you were to throw the dice, you can count how many times the number 1 came up on the top of the dice. So that's the small n, the number of times the event occurs. The number of times you throw the dice is the n, the large n, which is the experiment. And so an estimate of the probability is just the times that the event occurs divided by how many times you perform the experiment. If you want to look at the absolute uncertainty, you can take a look at the equation shown on the screen there. And the relative uncertainty is also shown, where P denotes the true probability. So in TracePro, if you're tracing a lot of rays, you want to know what your error account is for this particular calculation. And so the accuracy of the result is inversely proportional to the square root of the number of trials. So for instance, if you have a 10% error in your calculation on a irradiance map, for instance, if you want to reduce that to a 5%, you need to quadruple the number of rays that you're tracing to do that. And if you want to really go into the mathematics of the Monte Carlo technique, you can look at the numerical integration for the complicated multiple integrals that we're using. And that integral is a double integral, and you see it down below there. And this can be estimated by sampling the variables x sub j, computing g for the set of samples, and repeating this process n number of times, and then summing the terms to obtain the estimate of what the probability is going to be. So TracePro uses a couple of different variance reduction methods. The variance reduction techniques reduce the variance or uncertainty in the results that we see in TracePro using the Monte Carlo calculation after a given number of trials. Conversely, the number of trials needed to obtain a given uncertainty can be reduced. We do this by default in TracePro by using ray splitting. Ray splitting can be used in TracePro, and it can also be turned off. We also use a second variance reduction technique, and that's called importance sampling. So TracePro's default ray splitting method is a technique in which a ray strikes a surface and it is split into several component rays. And there's rays that are created for absorbed, spectrally reflected, reflectively scattered, spectrally transmitted, and transmissively scattered. And this all can happen at any surface at any time when a ray intersects that surface. The flux of the incident ray is also split, with a fraction of the incident flux assigned to each component ray according to the properties of the surface. The process of splitting is repeated at each surface so that we create a tree-like structure of rays. This process tremendously improves sampling in most cases, with a tolerable slowing of the ray trace. So if we look at this graphically, here we have a ray, it's incoming to this particular lens. And you can see the splitting going on as it reflects and transmits through this particular lens. This is where you would get ghosting, for instance, of this ray as it's coming through. And you can see that we're just going to keep ray splitting forever until it drops below the flux threshold or some other intercept that we set up in the ray trace options. So in terms of the second variance reduction technique, which is importance sampling, it's very similar to if we roll dice and we actually go through and we change the experiment a little bit. So take a look at a simple example. Consider a probability experiment to determine the chance of obtaining a 3 on the roll of a pair of dice. Using crude Monte Carlo, when we do this, we do the equation. We would roll the dice n number of times and count the number of times that the dice would come up to be a 3. We can compute that exact probability using the equation shown, which is 2 times 1/6 times 1/6, which equals 1/18. So that probability is 1/18 of the time. But what happens if we load the dice so that 1s and 2s occur more often, like a probability of 1/3 instead of 1/6? Then 3 would occur 4 times as often, and the estimated probability would now change to 1/4 times small n over large n. Okay? That is, we increase the probability of 3s occurring by a factor of 4, then divide the result of our experiment by 4 to obtain the true probability. This is the basis of importance sampling. We get more rays into an area where we want them to, but we flux weight them so that we get the right answer. This technique is applied in TracePro, causes scatter rays to go in a certain direction with a higher probability than they would if they were scattered at random. So we're loading the dice, pretty much what we're doing with importance sampling. So let's look at an example that we're going to use throughout this webinar. Methods to reduce noise. Well, if we trace more rays, which we're now able to do in the 64-bit compliant version of TracePro, and we use the multi-threading to trace more rays in much less amount of time, people want to trace more rays. But how many rays should we trace? For example, to achieve best results, accurate ray tracing of LEDs should be done with over 100,000 rays to reduce sampling noise and to find artifacts in a light pattern. If we use the sample system shown below with 31 LEDs and a light pipe that concentrates light to our target, we'll get something that as we see below there. But how many rays should we trace for the simulation? So I did a whole bunch of calculations here. I looked at 1,000 rays from each LED, 10,000, and 100,000 rays, and I set the irradiance map option to have a pixel count of 50. If we look at the flux for each case, we see very good agreement in terms of flux. 1,000 rays, 5,682 lumens. 10,000 rays, 5,657 lumens. And for 100,000 rays, 5,598 lumens. So that's pretty, staying in the same area, the same vicinity. But the luminous plots look quite a bit different. For 1,000 rays, the cross-section looks very, very noisy, as we can see in the top right figure. For 10,000 rays, we're starting to get an idea of what that curve should really look like. And at 100,000 rays, we definitely see what the curve should look like, and we're really starting to see a pattern emerge from the noise. But if we were to start off, how many rays would I start off with? Well, believe it or not, I'd probably start off with 10,000. If it took me just a few seconds, I'd add a few more rays, and I start looking for that pattern to emerge. Well, if we want to reduce the amount of noise, here's a good method for you. If we use smoothing, we can now smooth across the whole distribution, and we can look at the max flux and make sure it doesn't move too far down. If it does, if we're jumping a lot in terms of flux, then we know maybe we should be tracing more rays. If we look at the difference between the unsmooth curve here at the top, I believe that's unsmooth. I'm sorry, smoothing is on at the top and unsmoothing is on at the, in fact, no, bins are different. So the smoothing is put on the top. I would have to go back to the previous slide, which is the bottom one here. If you look at the bottom slide here, here's what it looks like unsmooth. That means this is just raw data. If we look at the top figure here, we now see it smooth. We notice that there's not very much noise in the calculation, and all the pattern looks very, very smooth between its transitional topography. So what can we do to look at even more further down into raw data? Well, we can ask for more pixels. If we change the number of pixels to 100, This now means that instead of having a 50 by 50 grid of buckets to catch all these rays, I now have 100 by 100. That's what's being shown at the bottom figure right here. That means we have 4 times as many bins. So when I double the number of bins or pixels to catch the rays, I'm actually increasing the number of bins or pixels 4 times. Okay? So now, if we want to catch as many rays as we did in the smaller bins, I'm going to have to trace 4 times as many rays to have the same number of rays in every single one of these bins. But you know, when I start looking at this data, even though I have smoothing on the bottom and the top, but I have 4 times as many pixels in the bottom, I now see that we're getting, once again, that noise back into this calculation. So we run a fine line between smoothing, number of pixels, and number of rays to trace to get the best answer. If we're interested in looking at artifacts, we probably want to increase the number of bins, and I'm going to talk about that in just a little bit here. But to reduce the noise, we want to use something like perhaps symmetry conditions. If we know our system looks the same top and bottom, right and left on our target, we can use quadrant symmetry. This is where we add the results from each one of the quadrants to each other and divide by 4, and then that's our result. This really helps out because we're doing random Monte Carlo ray tracing using random number seeds to get rid of that noise, because I'm now duplicating all the quadrants and all of those rays and adding them together. So it's like tracing 4 times as many rays without having to do any real work. We're just going to TracePro and into the options and specifying that I want symmetry in my calculation. So this allows the user to add illuminance and act like we're tracing a lot more rays without really tracing those rays. And we get a much more accurate answer, as you can see here. Look how much nicer the smoothing shows in this particular plot. Well, if we really want to reduce noise, we should trace more rays. So instead of using 100,000 rays, what happens when I go to the maximum that I can use on this particular computer in analysis mode? That's 1,000,000 rays per LED. So I'm going to have 22 million rays hit the target, and there's our final answer. As you can see, the lines are very smooth. There's very little noise in this plot, and you can see the nice oval-shaped target areas over, dropping off as we move away from the focus of this particular light pipe. So this is a really good answer. We know that the flux emitted flux looks really good. We know we have enough rays because there's quite a few rays in every single one of our buckets. This is an excellent answer. Now, are you going to wait 22 minutes to get this answer? I don't know. That depends on you. If you see the shape emerging and you can figure out what you want and this is good enough, then by all means, go for it. But on the other hand, you might want to try out TracePro's capability, and you do have that capability. Now, this was done on a 64-bit machine with 8 gigabytes of memory. So I had enough to do all of this in analysis mode. I'll talk about simulation mode in just a minute. But if you're looking to find artifacts, you need to turn off all that symmetry conditions, and you need to turn off and possibly have more pixels and turn off smoothing. So the illuminance map for 1,000,000 rays per LED looks a little bit different than the previous slide. We now have raw data, and we have the pixels set up 50 by 50, so I have 2,500 different bins to capture these rays. And if you're looking for artifacts, this is the plot you should use. Each one of the pixels or bins is 2 millimeters in size. How do I know that? This is a 100 millimeter square target with 50 bins. Divide one by the other. That gives you a 2 millimeter bin size. If you're looking for artifacts that are smaller than that, you're going to have to increase the number of pixels to give you those bins so you can see that particular artifact. So if you're looking for 1 millimeter artifacts in this particular plot, you're going to have to go to a number of pixels equal to 100, because then it's 100 millimeter square target divided by 100 to give you 1 millimeter pixel sizes. Okay? Simple equation, simple thing to remember, and that's what you're getting here. So we had a really nice plot here. We can see artifacts if we were looking for them, and this raw data gives us that. If you want to find artifacts of that 1 millimeter size, all you need to do is change that to 100, and you see now for that large ray trace of 22 million rays hitting the target, what the real data looks like for all of those. And you can see what smoothing's doing for us, and you can also see what the bin sizes do. Now I don't have the same number of rays in every single one of these, and so I may have pixels that look a little bit different from other pixels, even though I know from experience that these are going to be nicely well-defined areas. We don't see that. because we still haven't traced enough rays to give us that nice definition. How many traces would we have to trace? I'm probably thinking somewhere in the 10 million to 100 million rays. Most people don't want to wait for that. By looking at the previous slides, we should figure out what's going on here. Okay? Now, if you're looking for angular artifacts, we have to look at how a candela plot actually does the binning. So, for instance, for a rectangular candela plot, the bins are set up in angular space. And the plot points refer to the angular bins for the entire hemispherical plot, which is set for this plot to be 90 bins. How do I know? My smoothing factor in my candela options is set to 90. And this goes across a complete 360-degree extent. So if I divide 360 by 90, that gives me 4 degrees for each bin. So when I look at this, if I'm looking for an artifact that's a degree, I'm going to have to set this to 360, not to 90, because then, and only then, will I get that 1 degree angular bin that I'm looking for, and the ability to find that artifact. If we set the options to no smoothing and 180 bins, now we're plotting raw data at 2 degree increments. Now the plot has more noise, of course, even though we have a high number of rays, over 22 million, hitting the target once again, because you're using the same example. When you think about plotting the entire angular space, and you talk about 360 degrees by 180, that means if we're talking about 1 degree angular bins, there are 64,800 bins to collect rays in. A good ray number for each bin is 8 for decent data collection, especially at the outer angles. That means we need to trace at least 518,000 rays if the rays are evenly distributed across those bins. So that's what we're looking for over here. And you can see we actually are getting really good answers here, and that's really nice. We're not using smoothing, and the angular bins look quite good. So we're actually able to see those artifacts at 2 degrees. And if we wanted something better than this, we could go up to a full 360-degree plot points. Now, let's go back and look at that way to validate data. Look at the data without smoothing to determine if you have enough rays to create a good figure. Remember, I said we needed probably around 8 rays per bin. In the first case, when we traced 1,000 rays, you've got, if we were having 1 degree angular bins here, about 100 by 100, that would be 10,000. And I'd have 1,000 rays in 10,000 bins. That's just not going to give us very good artifact type information. But we should still get a good flux number. Now, if we look at the 10,000, finally the 100,000 ray trace, we finally see that answer emerging. You have the time to trace 1,000,000 rays per LED, and you're looking for artifacts in design, you should be able to find it. But 100,000 may not be enough because we may not have enough, and we may have too many bins for the number of rays we're putting in them, and the results might be too noisy. As you can see easily to the right there, with this particular setup where we have 222,564 rays, no, I'm sorry, 22,564 rays, we traced 100,000 rays total over here. It's just not enough. It's 1,000 rays per LED. It's just not enough for us to get a good answer. So we need to trace more rays if we're looking for artifact, but if we're looking for flux, this is okay. So I want to trace more rays. How do I do it? There are 2 modes in TracePro. There's analysis mode and simulation mode. In analysis mode, we keep all the information on every single intersection with every single surface in the model. In simulation mode, we only keep the information on those surfaces that we use and apply a surface property that says I'm an exit surface. So let's look at the 2 differences between these modes. Analysis mode stores all ray tree nodes, very memory intensive, allows and plots and tables for all model surfaces, permits ray history, display of rays, path sorting, and 3D irradiance. The simulation mode stores ray data incident on a single surface or multiple surfaces that you specified as exit surfaces. Stores ray data for missed rays. It uses a lot less memory. There are no ray histories, no ray display. Path sorting is available only in a file. And you have complete control of this. If you look over here in the simulation mode type options, which are underneath the simulation mode and the ray trace options, you can see what you can turn on and what you can turn off. And notice that most of this stuff goes to disk. So yes, you can look at ray history. Those ray histories that go to a file though, if it's checked. You can do path sorting, but it goes to a file, and you have to check this to get that. So remember, you can do a lot of stuff you do in analysis mode with simulation mode, but instead of storing it in memory, we store it to a file. That's all. Now you can run out of memory in both modes. So you have to be judicious about your flux threshold setting, using the task manager to monitor your memory use. And you might want to use TracePro's Raytrace report to see how much memory you're actually taking up. And if you do a small ray trace, you can see how much it takes. And then if you want to do 100 times that, just multiply that number, 100, times whatever the ray trace memory was and see if you have enough left. If you can actually do that. And that usually works out very, very well to see if you have enough memory. And if you do, you can do the ray trace in analysis mode. Now, ray traces of 50 million to 100 million are possible in simulation mode with 8 gigabytes on a medium PC. But in fact, you might be able to do up to about 31 million within analysis mode if you make sure that the other programs and everything else that you're using are not taking up a lot of that memory. So pretty much if I have 8 gigabytes on a machine and I'm running PowerPoint, and I'm running Outlook, and I'm running Internet Explorer, and I'm running a whole bunch of windows open, if you're going to do a lot of memory ray tracing, you might want to close those down because that uses up RAM memory as well. And you may want it for your ray trace. And please note that we've done 1 billion ray traces in simulation mode with a 16 gigabyte RAM system with large virtual page sizes. So if you have to do the simulation, you definitely can do it using simulation mode, using these options I've just shown out. So now we get to the point where, hey, I want to trace 50 million rays. How do I speed up the ray trace, and how do I reduce my memory requirements? Now, I've already talked a little bit about this. First of all, ray trace features may be turned off to skip some processing during the ray trace to save memory. So for instance, ray splitting is always turned on by default. And random rays, when we do a random ray off of a surface, is 1 for every ray that hits that surface when we have scatter. That could be upped. You could actually specify random rays to be 10. If you're really interested in scatter and looking for that type of scatter event, you might want to set this higher. But leaving it at 1 uses less memory and speeds up the ray tracing. Now, if you have a specific area that you want to go and send rays to, I have a variance reduction technique for that, and I'll talk about it shortly. Multiple random rays may be used to increase sampling, but requires a lower flux threshold. So remember, if you're going to up this number of random rays, you also have to go back and go to the Thresholds tab and reduce your flux threshold. Okay? Fluorescence ray tracing can be controlled and set to be run as a single or two-stage operation. For instance, you can use fluorescence to save the sources that are created by the fluorescence to a file, and that takes up less memory than the single-stage process. Also, you can change the random number seed to provide a new set of random rays for a ray trace. And you can save the irradiance map, say, to files, and then them all up together, and then divide to give yourself a much better answer. So that's another possibility, that you can actually do this in smaller chunks, add all the results together, and get your answer. More memories to speed up. Well, first of all, thresholds specify how many rays are ray traced and terminated. 5 thresholds can be set by the user. The flux threshold is probably the most important one. It's the fractional value of the starting flux. For instance, for illumination systems, I usually use a value of 0.05 to 0.01. And so, in other words, if you have a grid source, which each ray having a watt, and I go through a couple of components and it drops below 0.05, then that ray is going to stop where it drops below 0.05 and it's going to stay on that surface. If you do a report and you do a flux report, you're going to see that power on that surface being absorbed. I'm sorry, being terminated because of flux threshold. I'm sorry on that one. It is correct, it's flux threshold. The ghost analysis, the flux threshold should be around 0.001 because you want to see double ghosts, okay, which is double reflection ghosts. For stray light and importance sampling, you definitely want to go to like 1 e to the -6th. And of course, you have the capability to specify other thresholds like total intercepts, total scatters, random scatters, and optical scatters. Be careful about total intercepts. If you set the total intercepts to a system, say for instance a triplet system which has a source, 3 lenses each with 2 surfaces that the rays are going to go through, and then an image, that's 8 intersections with surfaces. Start off the source, that's number 1, goes through the front of the surfaces of the first lens, back surface of the first lens, front surface of the second lens, back surface of the second lens, front surface of the third lens, back surface of the third lens, image plane. That's 8 intersections. If I put a total intercepts of 6, I'll never have rays reach my target. So be cognizant that's what you're doing. But on the other hand, If you're not interested in looking at ghosting and you want to see the specular beam going through it, by all means, set your total intercepts to 8, and that's what you're going to get. Another thing, let's see. TracePro uses space partitioning to improve ray trace speeds via 2 types of voxelization. So first of all, what is voxelization? Voxelization is our method to split up object space where we make these 3D voxels and we write a list of all the surfaces in those voxels. And then when a ray goes into the voxel, we check only the surfaces that are in that list for that voxel. So this speeds up ray tracing. Now, by default, we use uniform, and this is set up very well when you have a system that has surfaces all the way through it, and you don't have like an elliptical reflector with a large amount of white space and then a target. For that type of system, you probably want to use Octree. I'll talk about that in a second. When you do voxel count, you specify, things get a lot faster when you have more voxels because you have less surfaces in these 3D spaces. But the audit time, which is done every time you do a ray trace, decreases with more voxels. It takes longer to write that list. So if you're just starting off, you can use fastest audit during initial model development and use faster ray trace when you're sure your model's correct and you're ready to ray trace large amounts of rays. With Octree, this really improves ray trace efficiencies for models with large distances between objects, which is especially good for systems with faraway targets. And I'll show you one in a second. Use the View Display Voxels after an audit to view the voxelization, like you see in this next slide. Here's where, in my options, my ray trace options, I specified Octree. And you'll notice that the voxels are all around my light pipe and around my target. This white space, I don't check for intersections of the rays with any surfaces in there, and this is a large area, so ray tracing is going to go faster in this area. And it's going to get sped up in this area because I have less surfaces in the voxels because they're more concentrated around my surfaces. So try this for yourself sometimes. Try the elliptical reflector example. Ray trace it using regular voxels, uniform, and Octree, and you'll see the Octree is much, much faster just for this reason. So if you want to speed up ray tracing and reduce memory requirements, there's another thing that'll help you, and that's underneath the Reports menu. This is your ray trace report. The ray trace report shows you just how much memory you've used, how much time it took to do the ray trace, and how much virtual space you have in terms of kilobytes on your hard disk. Okay, this is your virtual swap file. So for our sample system, where I used 100,000 rays for a total of 3.1 million rays, you can see that I have 239,816 kilobytes free when I got done the ray trace. And I used a total of over 8 million kilobytes of RAM. So I didn't have much left. I really couldn't increase that much more rays. I couldn't really double the number of rays because I would definitely run out of memory here. So we're not going to be able to trace many more rays before running out of memory for this particular analysis using 3.1 million rays. We can further check this while the ray trace is going on, because we can do that ray trace report after we're done. While it's going on, it's best to use the Windows Task Manager. This allows us to keep tabs on your memory and how well the multi-core ray trace is really taking advantage of all the cores in your computer. If you run into a memory simulation, as we show at the right, this is where I was doing 3.1 million rays for our sample system. You're probably going to want to switch from analysis mode to simulation mode, or you're going to run out of memory. You can see it right here. I've got 0 free memory almost at the end of my ray trace. I'm running out. I would have to now go to my virtual page file, which I've done, and even that I start seeing things go down to a crawl. You can see it right here. I have 7.76 gigabytes used of my 8 gigabytes. If you get to this point, the only option you have is to go to simulation mode or use some other method to do the ray trace. Because of this, there's a second mode of ray splitting in TracePro. This is to turn it off. And this mode is activated when we deselect ray splitting in the ray trace options. So in the ray trace options, if I uncheck the ray splitting, now I don't have the parent being split into child rays, each apportioned to the amount of power, of percentage of each one of the surface characteristics. So instead of splitting the rays at each surface, the total ray count is apportioned where the number of rays correspond to the surface property characteristics at each surface. So for this method, if we traced 100 rays to a lens surface that is 95% transmitting, 4% Fresnel reflecting, and 1% reflective scattering, here's how TracePro would handle it. 95 rays would be created that would transmit through the lens. 4 would reflect off the front surface, and 1 ray would be scattered randomly, depending on the random number generator. This technique uses a lot less rays, a lot less memory, speeds up ray tracing, and provides excellent answers when enough rays are traced. But there are caveats to this. Okay. First of all, using the second ray tracing method, we get very similar results for the illumination map for 10,000 rays per LED for our sample system. It only takes us 4 minutes instead of 21 minutes to do this calculation. We get almost the same results. We get a lot less memory. Look at that. I've got a lot more free after I do it. I use a lot less memory when I've done the calculation. So I'm using 1.6 megabytes of, 1 megabytes of memory. No, 1.6 gigabytes of memory instead of 3.8 for the ray splitting ray trace. But for this method to be accurate, you need to trace large quantities of rays. Tracing 100, 1,000, 10,000 rays will not give you anywhere near as good an answer as ray splitting. Let's take a look at this as a figure or graphically. With ray splitting on, you see there's a lot more rays when I hit the front surface of that lens. I've got 95 rays going through transmitting, but those other rays that are being shown here, that 5% in the ray splitting, they show up a lot more. There's a lot more of them. Therefore, I'm going to get better results when we're looking at this kind of analysis going on. But if I want just to look at the specular path, ray splitting turn on is going to give me the same answer as ray splitting off. See, I get the same number of rays in both of these modes. They equal each other. But when I'm looking for the forward part here, if I'm looking for this type of thing, and this is what I'm really interested in, ray splitting off is not going to give me a good number unless I trace lots and lots and lots of rays. Okay, so ray splitting is good for looking for, artifacts and things of that nature where scatter is involved and things of that nature. And ray splitting off is good when we're looking at the specular path. So that's what we were looking at here and previously with our sample system with the LEDs and the lighting. So ray splitting on or off is really good for that type of analysis. In fact, I would go with ray splitting off because I'm getting very good answers with ray splitting off and much, much faster answers and using much less memory. So if I look at that with ray splitting off, you see, look, all of a sudden I have lots more memory free when I turn my ray splitting off. I have all kinds of resources available here. I can see I got all kinds of resources. And I am using all of my cores when I'm doing the ray tracing. So I use all my cores when I split or I don't split. So there's a big speed up in terms of ray trace time to get an answer and less memory. So I can trace more rays. So ray splitting is great. It's a variance reduction technique. But on the other hand, ray splitting off can give me much faster answers and for the right application works much, much better. So what happens now? I've got ray splitting and no ray splitting. Is there a way I can really, do a lot more with scatter? Actually, you can. We have a second variance reduction technique, which is called importance sampling. And importance sampling is used to improve the sampling of random events without dramatically increasing the number of rays started. This uses the scattering distribution function as a probability density function to apportion a fraction of the scattered ray flux into a desired direction that you specify. This may be used for emitted, scattered, and diffracted rays only, or on surface sources, scattering surfaces, diffracting surfaces, or bulk scattering objects. If you want to do it on bulk scattered objects, you apply it to the object. For doing it on surfaces, you apply it right to that particular surface. So what happens here is that I have an incident ray that's going to strike a surface. First, you can see where the normal of the surface is in that direction. The specular goes in this area, but I want to look at the scatter, which goes into this area over here. So in other words, I have a delta area over here that I want to see the light go into. Well, there's no way that you can take a specular beam and throw it into this area. Specular beams do as they have to do. I mean, they're going to come out in a certain direction, and I can't force them towards a target because they won't go there. But scattered light will. Therefore, if I integrate how much scattered light goes into that entire area, this is where I'm going to see this entire BSDF or probability density. but the area I want fills in a certain amount of that area, which is shown over here. So I could then specify that the total scatter equals the integrated BSDF times the cosine of the angle times the delta of the area. And if I do this calculation and apportion my rays to this amount, I can get very good answers very quickly using importance sampling. Let's look at a little setup system here. I've got a lens. I've got scatter on this back surface over here, okay? So when rays hit this, my specular rays are going to go right through. My random rays can go in any direction, but mostly they're going to go into a ray direction, not towards this target. So what I'm going to do is I'm going to set up an importance sampling target on this surface that I'm going to send in this direction. And that's what you're seeing with these blue rays. These blue rays are importance sampled rays. They have a lot less flux than the random rays and the specular rays, of course, but they're apportioned depending on the flux on that particular surface, times the angle it takes to get them there, times the area that they subtend, that they go into right here. So there's our delta area, there's our delta cosine of the angle, and then all we need to know is the BSDF put on that surface. Now these rays are going to get a lot less flux than we normally have. Therefore, it's a good idea to set the flux threshold to a very, very low amount. Like I was saying, 1 e to the minus sixth. So in this little example, I want to send light from this surface, which is scattering, towards my target, which is over here, with an incoming light ray coming directly downward on top of it. So what I do is I grab that surface, the top surface, and I specify a target area towards my target. So I have towards, I put it on this surface that's the top of the box, towards this area right here, which I specify with a target center, a normal vector, and a target size. And right now this is a rectangular area, and I hit apply, and now there's an importance sampling target on this surface to send light in that direction. And when I do that, and I now do that particular analysis, look, I get all these importance sampled rays. So that's how you do it, using importance sampling. It's a great variance reduction technique. I'm getting all the rays out 1 per 1 for that surface to that target. In the analysis without it, I got nothing. No rays at all. So this worked out very, very well for me. You can do it for sources as well. For instance, I've got a spherical source. It's emitting in all directions, and none of them are going through my lens. But if I put an importance sampling target on the surface source itself and say I want to go in this direction, once again, we apportion using the cosine and the source emission to send one ray for every single ray sent out in that direction. So without having to trace millions of rays to get them to go through the lens, I can trace 100 and get 100 through. What's the beauty of importance sampling? It's ease of use, and it's easy to set these things up and get answers. So let's talk a little bit about, in terms of speeding up ray trace using a new method. There's a second method to really speed up ray tracing, and that's reverse ray tracing. That's where we specify targets that reverse their rays and search for the source. So a ray trace from all defined exit surfaces, defined surface sources, is allowed in the program. These sources are defined using apply properties dialog and applying an exit surface property and entering the number of rays for all the targets we want to reverse ray trace from. This is very useful in situations where importance sampling in the forward direction is difficult or impossible. For instance, in the design of illumination reflectors with a small source. So what does this look like? Say we have an elliptical reflector and we have an arc lamp, and it's emitting, and there are rays coming out of it, and they're striking a particular surface and going towards this target. Well, I'm going to get a few rays in that direction, and this exit surface is also out of plane, so it's very, very difficult for the system to get rays to that direction. So instead of forward ray tracing, I'm going to reverse ray trace. Right there, reverse ray trace. To do this, I grab the surface I want to reverse ray trace from, which is the observation disk target out here, and I'm going to say that that is an exit surface. So I make it an exit surface, and I specify the number of rays I want to reverse ray trace. That's it. And instead of saying I want to do a normal ray trace, in the ray trace result, I say do a reverse ray trace, and it will then do that. So for this elliptical reflector example, it takes 1 minute to forward ray trace. So the normal mode in TracePro, forward ray tracing, I trace 100,000 rays. I only get 361 rays to the target, as shown in the radiance map at left. But if I do the reverse ray trace, look, I get a much better answer. It takes only 4 seconds to reverse ray trace 100,000 rays, 1,822 rays reach the target. 6 times as many rays then are reaching the target, and it ray traces 15 times faster. So if I really want a good answer, it can happen very quickly. For this elliptical reflector example, when I've set it up like this, it takes 5 minutes to reverse ray trace 5 million rays. I'm getting 98,000 incident rays to the target, and I get a very, very nice answer very, very quickly. Think of how long it would take to do that same thing using forward ray tracing and how many rays I would get there. It would take a very long time, and you'd probably have to use simulation. So reverse ray tracing is the answer here for this particular problem. That's pretty much all I have for you today, and I'd ask that you send in some questions here if I haven't covered anything, and Dave's going to come on board and help me out.
Hey, thank you, Mike. Very good presentation. Don't have any questions on the board right now, so I'm going to open this up. To anybody that has any questions, please feel free, type them in the chat box or the question box on your GoToWebinar control panel, and we'll address them now. I guess, Mike, while we're waiting for some questions here, I guess one observation I always have when I'm talking about symmetry is that if you're going to apply symmetry, to make sure that the system you're applying it to should have symmetry. I have seen people make mistakes when they've applied rotational symmetry on an object that isn't rotationally symmetric. So it's one thing to watch out for when you're using methods like symmetry and smoothing to reduce the numbers of rays that you have to trace. Just make sure you actually are actually tracing a symmetric object. The one example I'm thinking about is somebody was doing a light pipe application where they had 2 light pipes that were offset from the center, and when it was rotational symmetry was applied, you wind up with one large blob of light instead of 2 individual spots of light.
Yeah, that is a definite problem. You don't want to do symmetry when you don't have those conditions. Yeah. And this is, by the way, if you haven't done reverse ray tracing before, this is where you would find that particular menu option in TracePro. And you would also see the reverse ray trace here would do that. You see where I've put up the 5 million rays. That would be using the apply properties and going to the exit surface where you would set that number of rays going in the reverse direction. So if you haven't done that before, try it out with maybe one of your systems. See how that works out for you.
You need to make sure too with the reverse ray trace that your sources are surface sources. Reverse ray trace does not work with file or grid sources. So just one quick note there.
That's correct.
Okay. Well, I'm still not seeing any questions, so I'm thinking you did a very good job here, Mike. Put a last call out for questions. I don't know if there's anything else you want to add, Mike.
Well, one other thing is that if you want to increase your virtual page size to have some of these big ray traces, go to your control panel, your system area, go to the advanced system settings that you see over here, the advanced system settings, go to your advanced tab, and you can change your performance calculations. In fact, if you go to the custom over here and you set that, you're going to see that what your virtual memory is. And I've gone to the advanced tab here, and that's going to show you how big your total paging size is. If it's not big enough, you can increase it, and that'll allow you to do larger ray traces, just so everyone knows. That's pretty much all I have for everyone.
Okay, I guess my last comment was when you were talking about defining the number of rays to trace is to make sure you're looking, if you're doing an irradiance map, looking at the number of rays actually getting to the irradiance map as opposed to the number of rays you're starting from the source, because that's really where you need to get enough rays on that irradiance map.
Very true.
Yeah. But okay, so I don't see any questions, so I guess we will wrap this up for today. I'd like to thank everybody for coming and attending. Also like to thank Mike for the excellent presentation today. And we'll look forward to seeing everybody with next month's webinar.
And once again, we'll have this whole webinar up on our webinar section of the website, so you can see it later on if you want to look at it a second time, and these slides will be up there as well. Okay. Thanks again. I'm going to stop the recording, and thanks for all of you for attending.